Assalamualaikum and good day. Welcome back to BQS 552 Construction Technology 4. In this class, we will learn Chapter 2, Soil Improvement and Stabilization Technique. There are many engineering problems in the form of slope instability, bearing capacity failure, or excessive settlement could occur either during or after the construction phase due to low shear strength and high compressibility of the soil. This can be seen from the illustrations. At the end of this chapter, it is expected for the students to be able to identify the reasons for soil stabilization, able to identify factors affecting the strength of the stabilized soil, and able to determine the soil stabilization techniques. There are many objectives of soil stabilization. Among them are soil erosion control. Soil erosion control is the process of minimizing the potential for soil erosion. Erosion control measures have proven to reduce erosion potential by stabilizing exposed soil and reducing surface runoff low velocity. Another objective is to increase the bonding between grains, increase the mechanical strength and stability of the soil. It is also important to reduce the volume of voids, which is minimizing the porosity. And if the void can't be reduced, the void that cannot be eliminated need to be filled to reduce permeability of the soil. Permeability is how easily liquid and gas passes through something. In this case, for example, how fast water flows through porous soil. Factors such as organic matters, sulfates, sulfides, compaction, moisture contents, temperature can affect the strength of the stabilized soil. The first factors, which is the organic matter, it is the organic content in the soil that can affect the stabilization process. For example, large amount of organic matter can lower the pH of the soil to be stabilized after reacting with the additive in the material that are being used during the process. It is therefore necessary to determine the percentage of organic matter in the soil so that an allowance for the resultant reaction can be made when designing the soil stabilization process to be used. The second factor is sulfate. The use of calcium-based stabilizer in sulfate-rich soil causes the stabilized sulfate-rich soil in the presence of excess moisture to react and form calcium sulfoaluminate, the product which occupy greater volume than the combined volume of reactants. However, excess water to one initially present during the time of mixing may be required to dissolve sulfate in order to allow the reaction to proceed. The third factor is sulfides. The existence of sulfides within the soil can affect the choice of the product to be used during the soil stabilization process. For example, it may be unwise to use binder containing calcium carbonate in case the soil has sulfides in it, because sulfuric acid will form and attack the stabilized soil. In many waste materials and industrial byproducts, sulfides in the form of iron pyrites may be present. Oxidization of pyrites will produce sulfuric acid, which in presence of calcium carbonate might react to form gypsum. The hydrate sulfate to form, and in the presence of excess water may attack the stabilized material in the similar way as sulfate. Gypsum also can be found in the natural soil. The fourth factor is compaction. Stabilized mixture has lower maximum dry density than that of unstabilized soil for a given degree of compaction. The optimal moisture content increase within increasing binders. In cement stabilization soil, hydration process takes place immediately after cement comes into contact with water. This process involves hardening of soil mix, which means that it is necessary to compact the soil mix as soon as possible. Any delay in compaction may result in hardening of stabilization soil mass, and therefore, extra compaction effort may be required to bring the same effect. That may lead to serious bond breakage and hence loss of strength. Stabilized clay soils are more likely to be affected than other soils due to alteration of plasticity properties of clay. In contrary to cement, delay in compaction for lime-stabilized soil may have some advantages. Lime-stabilized soil require mellowing period to allow lime to diffuse through the soil, thus producing maximum effect on plasticity. After this period, lime-stabilized soil may be remixed and given its final compaction, resulting into a very remarkable strength than the otherwise. The fifth factor is moisture content. It is also important to measure the moisture content of the soil before the soil stabilization process can begin. Different soil stabilization products such as quicklime and cement require varying amounts of moisture to produce the desired results. The level of moisture found may influence the choice of the product to be used. Failure to do so can result in unsatisfactory results due to incomplete reaction between the soil and the products that have been used to stabilize the soil. The sixth factor is temperature. The reaction between the soil and the binders used during the stabilization process have temperature requirements. For example, cement will take long to gain strength if it is applied to the soil when the temperature is below the optimum level. Conversely, during curing period will be accelerated if temperatures rise above the desired level. Rapid curing can result in lower strength. It is therefore prudent to select a time when the temperature will be just right for the products that are going to be used during the stabilization process. The last factor is freeze-thaw and dry-wet effect. Stabilized soil cannot withstand freeze-thaw cycles. Therefore, in the field, it may be necessary to protect the stabilized soil against frost damage. Shrinkage forces in stabilized soil will depend on the chemical reactions of the binder. Cement stabilized soil are susceptible to frequent dry-wet cycles due to diurnal changes in temperature, which may give rise to stresses within a stabilized soil and therefore should be protected from such effects. Importance of soil stabilization. Structure need a stable foundation for their proper construction and lifelong durability. All the loads came from structure will be transferred to the foundation, and foundation needs to rest on soil, ultimately transferring the whole load to the soil. If weak soil base is used for construction, with passage of time it compacts and consolidates, which result in differential settlement of structure. It may result in cracks in structure, which can have catastrophic effect if the settlement is too much. Soil improvement is generally achieved by adding binders. Soil improvement is used to address handling or compacting problems resulting from high plasticity or high water content. Such soil can be improved by mixing with lime. Adding lime to clay provides three important benefits, which are breaking down clay interparticle cohesion, reduced plasticity, its ability to undergo deformation without cracking or fracturing, and another one is moisture content reduction. Soil stabilization refers to the procedure in which a special soil, a cementing material, or other chemical or non-chemical materials are added to natural soil, or a technique used on the natural soil to improve one or more of its properties. It is required when the soil available for construction is not suitable to carry structural load. Soil stabilization is used to reduce permeability and compressibility of the soil mass in a structure, and to increase its shear strength so that increase the resistance to change in shape. Soil stabilizer interaction vary with soil types, and so does the extent of improvement in soil properties. Developing a common procedure applicable for all types of stabilizer is not practical because there are many types of soil. Soil stabilization is important because it reduces permeability and compressibility of the soil, increase shear strength, enhance bearing capacity of soil, and improve natural soil for construction. Soil characteristics, including mineralogy, gradation, and physiochemical properties of fine-grained soil, influence the soil additive interactions. Hence, stabilizer selection should be based on the effectiveness of given stabilizer to improve the physiochemical properties of the selected soil. Some types of soil may be used in their natural state, which other may be excavated, processed, and compacted in order to serve their purpose, so the properties, characteristics, and behavior of the soil must be known in order to design or construct projects involving the use of soil. The preliminary selection of appropriate additives of soil stabilization should consider soil consistency and gradation, soil mineralogy and composition, desired engineering properties, purpose of treatment, mechanism of stabilization, and last but not least, environmental conditions and engineering economics. Soil stabilization results in engineered materials that provide improved static load resistance, improved resilient behavior under dynamic load, reduce its permeability, improve freeze-thaw resistance. Freeze-thaw weathering is a process of erosion that happens in cold area where ice forms. A crack in a rock can fill with water, which then freezes as the temperature drops. As the ice expands, it pushes the crack apart, making it larger. Stabilization of soil can be done using mechanical stabilization or stabilization by using admixture. The first technique that we are going to look into is mechanical stabilization. Mechanical stabilization is the process of improving the properties of the soil by changing its gradation, which is changing composition of soil by adding or removing different soil particles. This process includes soil compaction and densification by application of mechanical energy using various sorts of rollers, rammers, vibration techniques, and sometimes blasting. The stability of the soil in this method relies on inherent properties of the soil material. Two or more types of natural soils are mixed to obtain composite material which is superior to any of its components. Mechanical stabilization is accomplished by mixing or blending soil of two or more gradations to obtain material meeting the required specification. Ground treatment is basically the process of compaction of the deposited infill. The method of ground improvement can be used according to the soil types. Vibration methods can effectively use for rapid densification of saturated non-cohesive soils. Vibration and shock wave in loose deposits of such materials cause liquefaction followed by densification accompanying the dissipation of excess pore water pressure. Some of the most adopted vibration methods are blasting, vibrating probe, vibratory rollers, vibro displacement, compaction piles, vibro flotation, heavy tamping, and many others. The method of compaction can either be dynamic compaction, vertical or weak drain, or using the vibro flotation technique depending on the ground condition. In the vicinity of the deep slip surface, vertical bored sand or gravel-filled drain, known sometimes as sandwicks, can be used to drain perched permeable stratum. The proprietary system, consisting of sand-filled geofabric tubes which can be lowered into a small diameter pre-filled holes, is used marketed for this product and has the advantage that has the strength of the fabric helps prevent the drains being severed by small downslope movements. Alternatively, horizontal or near horizontal bored drain can be installed from the toe of the face of the slope. Drains of this type are usually lined with a perforated or permeable materials such as no confines concrete rather than filling with granular medium. For maximum effectiveness, deep drain should extend well beyond the point at which the reduction in pore water pressure is required, probably as much as 2 or 3 times the drain spacing. Vibro compaction, also called vibroflotation, uses large vibrating mandrels to penetrate, displace, and compact the soil. When the mandrel is removed from the ground, the subsequent void is filled with stone. The mandrel is then forced back through the stone, further displacing and compacting the ground stone. The method that produces stone columns in the ground compacts the surrounding strata, enhancing the ground bearing capacity and limiting settlement. Typical application include support of foundations, slab, hard standing, pavement, tanks, or embankments. Soft soil, man-made, or other strata can be reinforced to achieve improved specification requirements, while slope can be treated to limit the risk of slip failure. The allowable ground-bearing capacity for low to medium-rise building and industrial developments are in the region of 100 to 200 kN per meter square. Beneath tanks on embankments or slope of 100 kN per meter square can also be achieved. Ground condition may allow heavier loads to be supported. The high-powered mandrel penetrates the ground in a vertical plane to the design depth. When the mandrel is extracted, the resulting bore is filled with suitable aggregate or stabilized solid. These are compacted in layers around 200 to 600 mm increments. The shape of the mandrel tip is designed to ensure high compaction of the stone or stabilized soil column and surrounding strata. The taper on the mandrel causes increased densification of the strata. Dynamic compaction and consolidation using tamping system can enhance the ground condition up to a considerable depth. The ground is consolidated by repeatedly dropping specially designed tampers into the ground. Ground conditions suitable for dynamic compaction include natural ground soils, made-up ground, and landfill refuse sites. The technique can also be used as part of more significant earthwork operations where the ground is built up in layers, compacted, and consolidated. Where fill is built up in layers, the fill may take the form of unmodified materials as previously excavated, or soil which are modified or stabilized using additive such as quicklime and pulverized fuel ash (PFA) or cement. To achieve the desired effect, several passes may be required. Carefully monitoring and testing is required. Grit levels may need to be taken before and after each pass. Trial drops should be taken to determine the optimum treatment regimen. Monitor the imprints and depth, and measure pore water pressure as necessary. To determine the allowable bearing capacity, accurate measurements are taken of the penetration achieved by application of particular energy, known load from a known height. Analysis of the levels can be used to calculate the amount of void closure and the degree of densification. Using dynamic compression, bearing capacity of 50 to 150 kN per meter square can be achieved. Greater bearing capacities may be achievable, it also depending on the ground condition. Two systems are commonly used. The first uses a flat bottom tamper, and the alternative, more modern method uses cone-shaped tampers. Flat bottom tampers can be slower and tend to create more noise and vibration than the cone system of tamping. Modern methods tend to use vertical guiders to control the fall and rise of the tamper. With traditional method, the load tamper was simply attached to a cable. When lifting and lowering the weight, time had to be allowed for a tamper to stabilize. Different shaped tamper heads are available with a variety of weight depending on the degree of the consolidation and compaction required. For example, we have long cone, flower pot cone, multi-point cone, and traditional weight. The illustration shows a typical pattern of work. 3 passes are used in this example to achieve the required compaction and consolidation. Initial tamping is undertaken using single point tamper. The tamper is up to 2.5 meter long with a mass of 10 tons. The ground is tamped on a grid, and the objective of densifying deep layers. Subsequent tamping is undertaken using multi-pointed tampers. The multi-point tamper improves ground consolidation at a shallower depth. Next, we have Foccofra dynamic compaction, or CDC. It also called rapid impact compaction, RIC. This method consists of placing the foot on the marked location. After positioning, the hammer is released from the lifting frame to be able to move freely during compaction. The compaction process is started by lifting of the weight to the predetermined height, after which the hammer is dropped onto the foot, which remain in contact with the ground. This process is repeated until the stop criteria set by the geotechnical engineer are met. After completion, the hammer is connected to the frame and lifted to the next compaction location. A dense grid between 2 and 4 meter is used to create homogeneous compaction. Preloading or surcharge is an economical and effective soil improvement method that can reduce settlement and increase the bearing capacity of soft soil. In other words, preloading accelerates settlement of the soil before the construction of the structure. Surcharge load is used to expedite the consolidation of the soft soil, where the backfill soil is placed on top of soft soil for a certain period of time. The consolidation is the process to drain out water from the soft soil. The backfill represents the load of the structure to be constructed, so that when the structure load is put on the soil foundation later on, the movement of the soil foundation is minimized. Commonly, the combination of preloading and vertical drain is used to make the method more effective. The function of vertical drain is to shorten the duration of soil treatment. Preloading forces water out of the soil matrix, facilitating soil consolidation. Preloading with a vertical drain permits the soil of a cheaper, shallow foundation. The soft soil is characterized by low strength and high compressibility, and hence possess low bearing capacity. Our lesson today. Thank you for your kind attention. I will end the recorded video with the quote from John Maxwell. There are 2 kinds of people in this world: those who want to get things done and those who don't want to make mistakes.